speak. So I'm going to talk about optimal polynomial approximants in some slightly more general sense than which they've been talked about in the existing body of literature. Okay, so let's get situated. So for this talk, I want to be in a Hilbert space, and this Hilbert space is going to be a Hilbert space of analytic functions on the unit disk. I'm going to ask a few extra properties. The first, that the polynomials are dense. Okay, so I'm going to denote the polynomials by this calgraphic P. Secondly, I want the forward shift to be bounded on H. So this is just multiplication by the independent variable. So I'm always going to call this independent variable Z. And next, I want point evaluation to be bounded on D. So what I mean by this is that the linear functional of point evaluation for all points in D is a bounded linear functional on H. Okay. And so by the Riesz representation theorem, we know that there's some unique element, Kz, for each Z in D, so that when I take F, inner product Kz, I recover the value of F at Z. Okay, and this element Kz is called the reproducing kernel at Z. Okay, so thanks, Nikos, for giving the definitions for the Dirichlet type spaces in your talk, because for example, some of these spaces you could think of are these DS spaces, these Dirichlet type spaces, or just classically the Hardy space, H2. Okay, so these are, this was when S equals 0 in the Dirichlet type spaces. So just to have something to keep in the back of your mind, you can think of those spaces. Okay. So the main object of study for this is going to be cyclic functions. So we take a function in H and we say it's cyclic in H for S if this space bracket F, which is defined to be the closure of the span of the monomials times F, in H is equal to all of H itself. Okay, so this just is the polynomial multiples of F closed up in H. Okay, so I'll call this bracket F, or I might say the subspace generated by F. Okay, and this is always a shift invariant subspace. So S acting on bracket F is back in bracket F. Okay. Quick note is we have some equivalences. So let me just note, I guess the big picture question here is what are the cyclic functions in H? So given H, what are the cyclic functions there? So that's what we're interested in answering. I won't answer, that's a very difficult question, but we're gonna try to study cyclicity nonetheless. Okay, so we have some equivalences. The first is that F is cyclic, and the second is that 1 is in bracket F. Okay, well, if F is cyclic, then bracket F is all of H, so certainly 1 should be in there. If 1 is in bracket F, you can consider bracket 1, which is just the closure of the polynomials, and we're asking that H has as a dense subset the polynomials. So bracket 1 will be contained in bracket F, so if 1 is in bracket F, then F is certainly cyclic. And lastly, if 1 is in bracket F, then we should be able to approximate 1 by some polynomial multiples of F. So namely, there should be a sequence of polynomials, Pn, so that the norm of Pnf minus 1 goes to 0. Okay. So this norm here is what we want to study. Okay, and maybe the first question one might ask is, can we find a sequence of polynomials so that this norm Pnf minus 1 decays optimal? And the answer to that question is yes, and it's given by what we call optimal polynomial approximants. Okay. So I'm going to let this calligraphic piece of n denote all of the complex polynomials of degree less than or equal to n. And I'm going to take f and h. And I'm going to say that Pn star is the nth optimal polynomial approximant to 1 over f if Pn star solves this minimization problem. Okay, so why do I say 1 over f? Well, morally, if Pn star looks like 1 over f, then in the norm here, we have 1 over f times f, which gives us 1 minus 1, so the norm of that is just 0. Okay. The first thing we should note, though, is that Pnf is a closed subspace of H. So this, if we call this star, this norm, this minimization problem, this is asking us for the nearest element to 1 that is a polynomial multiple of f. Okay, so since we're in a Hilbert space, this is just given by the orthogonal projection of 1 onto the subspace. So I'm going to use this capital pi to always mean orthogonal projection, and the subscript is the subspace in which I'm projecting onto. Okay. So this is sort of the classical optimal polynomial approximation problem, if you will. And I just want to note that there's much work done here when the reproducing kernel at 0 is equal to 1, so in spaces where that's true, and where the monomials are orthogonal. Okay. So what about other spaces, right? What about spaces where we don't have the reproducing kernel 0 equal to 1, or we don't have the monomials orthogonal? So, for example, let's take some weight in L1 of the circle. A classical theorem of Szego says that this space P2 of V, which is just the span of the analytic monomials, closed up in L2 of V, and so I mean L2 of the circle with respect to V. This is equal to all of L2 of V, if and only if the integral of log V is negative infinity. So if the integral of log V is greater than negative infinity, we know that in that case, there exists an H2 cyclic function M, so that the modulus of M squared is V, and P2 of V is isomorphic to 1 over M H2. And we have this equality of norms. So if we put F equals H over M and P2 of V, it follows that the norm of PF minus 1 and P2 of V is equal to the norm of PH minus M and H2. And this is for any polynomial P. Okay. So the moral here is that approximating 1 by polynomial multiples of F in P2 is the same as approximating M by polynomial multiples of H in H2. So this is motivation, one motivation for wanting to replace, say, this function 1 by some other cyclic function, say M. Okay, and you might think, well, we know the story of cyclicity in H2, so we should know the story of cyclicity in P2, and my answer to that would be touche, you're correct. But there are other reasons why you might want to replace, say, in general, some PF minus 1 and with, say, some PF minus G, where G is some other cyclic function. And I'm going to speak kind of loosely here and just say that 1 is very nice. So it's a very nice cyclic function. So the thought is that if we can replace one by, say, G, which is cyclic but worse behaved in some way, this might illuminate some of the properties of F that contribute to it being cyclic or not cyclic. Okay, so that's more of a big picture, future work observation. Okay, so but what I want to dig into now is general approximants, and what I mean by general is approximating functions other than one. Okay, so polynomial multiples of some given function f, how close can I get to one? Right? And so the corresponding definition, of course, is just going to be, we're going to grab two functions, f and g and h, and we just want them not to be orthogonal. And we say that qn star is the nth optimal approximant to g over f if qn star solves this same minimization problem. Okay, and I'm using qn star here just to denote that g is not necessarily 1. So, okay, let's see. So let me note here, for the same Hilbert space reasons, that qn star f is just going to be the orthogonal projection onto pnf of g. Okay, so the way that I like to think about this is you have these nested subspaces, these pnfs, and we're just projecting orthogonally onto all of these subspaces, and we're seeing how close we can get to G with these projections. Okay, so in general, we might ask, if we want to study cyclicity, what can be said about this sequence qn star? Okay, that's a very broad question, so I want to bring it down to say, for example, can we have a sequence of finite number of distinct elements in this sequence, or can the sequence stop in some sense? And this has a little more natural motivation that if I have time, I'll come back and talk about. So to formalize this stopping, we say that the sequence qn star stabilizes at qm star if qn star equals qm star for all n greater than or equal to n. Okay, so this just means when you're looking at these projections that eventually you just hit a wall, and you hit a wall at this mth projection, right? So you get no closer to where you want to go by adding in higher order terms to your approximation. Okay. So I'm going to take a slight detour here, and I want to talk about inner functions, generalized inner functions, because this plays a part in the story. Okay, so we take a function f and h, and we say f is h inner if f inner product z to the k f is 1 when k is 0, and 0 when k is greater than or equal to 1. Okay, so namely f has norm 1, and it vanishes against all of the iterates of its iterates under the shift in the inner product. Okay, so I want to make a note here that f being h2 inner, which is the classical inner function, this corresponds to f being 1 in modulus almost everywhere on the circle. And these two definitions are equivalent. This was first given, this definition was first given in the Bergman space by Allemann, Richter, and Sundberg. And it generalizes really to any space H in which we're considering here. So what do OPAs and inner functions know about each other? Okay. Well, there's a nice theorem by Beneteau, Fleeman, and Covenson, Secco, and Sola that describes this. Okay, so it describes it in spaces H, where the reproducing kernel at 0 is equal to 1. As I mentioned, this is sort of where most of the body of literature has been situated. So if we take F in H with F of 0 not equal to 0, that's just saying K0 and F are not orthogonal. We let Pn star of the OPAs to 1 over F, then F is H inner, if and only if Pn star stabilizes at P0 star. So this means, well, I'm looking at these projections and I can get no closer to 1 than just some constant multiple of F. Okay, so the connection here sort of between OPAs and inner functions is stabilization. Okay, and what we want to do is somehow generalize this. So we want to generalize this maybe where Kz of 0 is not equal to 1, and maybe generalize it where we take some other function or some other point in our sequence that isn't at 0. All right, so what's the connection between stabilization of general OPAs and inner functions? Okay, so a generalization of the previous theorem would sort of give this. Okay. So what we need is one more definition and to be able to connect these things. And this definition is what I will just read aloud is KSF. I don't have a name for this set. I'm open to suggestions if anybody has any. And it's just the functions in H, so that H z to the KF, the inner product, is 0 when K is greater than or equal to 1.
You may be frozen or maybe I'm frozen.
Ah, okay. Let me.
Oh, I can see things moving.
Yeah, everything's fine for me too.
It seems to be working now.
Okay.
Anyway, sorry.
Okay, so this space KSF, alternatively, can be viewed as the orthogonal complement of the subspace generated by the shift acting on F in H. So it's kind of like a model space, if you will. But okay, so the point here is that we're going to take our general function that we're trying to approximate, and we're going to let it be in this set, because then that gives us a way to connect the stabilization of the OPAs and inner functions. Okay, and that's given by this theorem. Okay, so again, we take two functions, f and g, in H that aren't orthogonal. We're letting Qn star be the OPAs to g over f, and then we have the following are equivalent. Okay, g is in KSF, and the projection of f, the projection of g onto bracket f is Qm star f. Right? So this is stabilization. Okay. Secondly, we have Qm star f itself is just in KSF. And now we have the inner characterization, that is Qm star f over the norm of Qm star f is H inner. And we need a little bit more help here. We need that Qm star f inner product z to kf is 0 for k between 1 and f. So let's see, about 1 minute. So I'll say something. So morally, what's going on here is that if when you're trying to approximate, say, g by polynomial multiples of f, and you have these approximants qn star f, say, so these are just the projections. If you're taking these projections and you hit an inner function, you sort of stop. You can't get any closer to the function g. Okay. And so just a word about the proof. Most of it is just baked into the definitions. The only place that you really need any work is 3 implies 1, and you just need some algebraic tricks there. Okay. And lastly, just to kind of bring it full circle, when G equals 1, or sorry, when G equals just the reproducing kernel at 0, you automatically get this, and you automatically get this. So you have a bit of a nicer theorem statement. Okay. So I will